Alright, so one of the problems on the test that gave me a bit of trouble was the problem 3, which was the calculation. You have to write the code to calculate the craft's velocity and position. And alright, so this is just part A and B, because C and D didn't really give me that much trouble. Alright, so part A says add the necessary statements to specify the mass and the initial conditions. Alright, so if you look at the problem, it says the spacecraft has a mass of 15,000 kilograms, with an initial position of negative 5.8, negative 7, blah blah blah, moving with an initial velocity of negative whatever. Okay, so this is pretty straightforward. All I have to do is just create variables that have the parameters that are given in the problem. So a nice variable name would be mass equals 15,000. Alright, next thing. Now it says that you want to, you need to put the initial conditions. So they give you two initial conditions of the problem. The initial position. Oh yeah, I forgot to add one thing. And also in the problem, this is already given. But, let's put it right here. Craft equals sphere. 6. Alright, so yeah, there we go. Now it's all good. So anyways, yeah, so I added the mass, right? So mass is 15,000 kilograms, that's in the problem, so that's easy. Next thing you want to add is the initial position. So a good name for that would be like, so to do that you have to call on the craft, and to access its position, you do craft dot position, and then set it equal to a vector, and that vector is equal to negative 5.8 e times 10 to the 7th, 5.4 times 10 to the 6th, and 0. And now one last initial parameter that it gives you is the velocity. So let's just, and surprisingly it's not too much harder to add the initial velocity. Do craft dot velocity, or vel, equals vector. And then this the problem gives you negative 604 27950. Alright. And that is it for part A. That's all you have to do. Alright, now part B is where it gets a little tricky. You have to fnet equal GG. No! Oh, how do I do this? Alright, so now what we need to do is write the loop to like calculate the velocity and the position. So right now, like, first thing let's use the momentum principle, right? So then what will be the net force on the system? And you have to refer back to the problem. And the problem explicitly states that there are no interactions on the craft. And what that means is that all the pushes and pulls even out, and then essentially, so the net force is going to be 0. And that just takes, you have to just read the problem. That's pretty simple to interpret. So the net force is 0. So now the next thing you have to do is use the momentum principle. So remember, what is it? Delta P equals Fnet times delta T. So, but in this case, we're going to have to write it in terms of velocity. So we're going to have to divide by mass. So if we divide by mass, we're going to get the craft's velocity is equal to the previous craft velocity plus the net force divided by mass, which is essentially acceleration. So the acceleration times time times delta t. All right, so this is essentially, so this step is just the momentum principle divided by mass. That's all it is. The next step would be then to calculate the position. So we'll just call the craft.position equals the previous craft position plus the craft's velocity times dt, so times time, times the change in time. And the last thing we have to do is actually increment the loop. We need to like somehow code the progression of time. And the way we do that, we'll do t equals t plus dt. And that essentially allows time to go on. So it's going to increment the time, and when t is less than 305 whatever something, it's gonna end the loop. So there you go. That's A and B, and I hope that helped.